start with motivation. So like that. So the first part is going to be motivational, and it's going to be a little bit vague. So I want to also indicate the connections of complex analysis to other fields. So I will talk a little bit about that. And the first thing is I'm going to talk about is what's called a random walk. A lot of you know what that is. So what I want to do is I want to remind you what uh, random walk on sorry, just a second. Random walk on graphs. So okay, so let me just, I don't know how this pointer thing works, even not like that. I'll just start doing this. So imagine you have a random walk. Actually, this is the wrong one, but that's fine. So you have a grid and you start a random walk. What does a random walk do? It with probability, in this case, the probability 1/4, it goes up, down, right, or left, and independently on each step. So what you get is something like that. And one of the questions we want to know is how often does this random walk come to the origin, where it started, or where it come to any compact set. Okay, so in this case, you see that it doesn't really go too far, but that's kind of like you may say that's because you're doing it on a small grid, but in reality, that kind of also indicates the truth that if you start a random walk on a grid z cross z, it's actually what's going to happen. It's going to be recurrent. Okay, so what does recurrent mean? Right now, I think I can go. Right, so random walk is called transient if it approaches infinity almost surely. So what does that mean? It means that if you you look at the, let's say, some finite collection of paths of length n, among those you kind of think of them as a measure. You look at them with uniform distribution, and you look how many of them go to infinity. When I say almost surely, it means that the number of those which go to infinity, or that they don't return to a compact subset infinitely often, the number of those goes to zero, right? So that, well, approaches infinity means the ones which don't approach infinity happen with zero probability. So that's the transient, and the recurrent, it means avoid infinity almost surely. So the returns to compact subsets infinitely often. So in these two examples, in the first example we saw it was z cross z, and it turns out in that case what happens is that the particle comes back to the origin infinitely often. It basically doesn't go to infinity. So that would be an example of what's called a recurrent random walk. Okay. Now you might say, what does that have to do with complex analysis, right? So just bear with me. So here is another example. Well, I just said random walk is recurrent on the, well, okay, that's a question which I answered. So which one is it, recurrent or transient? Recurrent, right? Okay. So now this graph, look at that. Does that remind you of anything? Start with a pentagon and add more pentagons. And then next to each pentagon, add another pentagon and so on. What do you think is going to happen? So you can start now a random walk on at any of these points, and then now you're doing the probability being 1/3, and with the same probability going one way. So what do you think? Oops. What do you think? Is this recurrent or transient? So this turns out to be actually, who's doing hyperbolic geometry? Some people are, right? So does that look like a tessellation of the hyperbolic space? If it does, that means it's transient. It means it's going to go to the boundary, okay? So that's what that means. Okay. Now, well, from that picture, I deliberately drew that picture so that you can't really see that random walk is gonna go to infinity. But in reality, that's what happens in this example. Okay, now let's see what in terms of complex analysis, what we said, like we have this point at infinity, and when I say, again, all of this a little bit not precise, but you can make it to be random walk is recurrent if infinity, the paths don't go to infinity, so infinity is small, it's being avoided, and it's transient if infinity is large, so you can't really avoid infinity. So in our examples, you can parameterize z cross z approximates the plane. So infinity is in complex jargon has zero capacity. And in the other case, when you extend it to infinity, what you get, you fill up a disk. So that's kind of a large set. So infinity is big, and then you actually have to go there. So, right. So that's kind of saying we're talking about the recurrence in terms of a point being small or large, which I'll define a little bit in more detail in a second. So the next point then is, so you can do the same thing on an arbitrary surface, a Riemann surface. So here's an example of a surface. On it, you can see there is a grid. So you can think of doing a random walk on that grid, and then you can ask, does that point, a random walk on a grid that approximates the surface, does that go to infinity, whatever that means, does that escape every compact set or not? So is that transient or not? So, and then the complex analysis jargon says we say Riemann surface is parabolic if Brownian motion, or which is the same thing you can think of random walk on a very tiny grid is recurrent. Okay, so that means the boundary is small. Equivalently, x is parabolic if infinity is small. Now, for those of you who know function theory, it means that there are no non-trivial bounded harmonic functions. Okay, so that's a different way. Or the actually no green function, no Green's function. So this one actually doesn't have that property. It's not parabolic because of these funnels here. If it had only cusps like that, then it would be parabolic. Okay, now let's go to a little bit of complex analysis. What is the meaning of a point in this particular case, infinity being small? What's the meaning of that? In our talk, we're going to talk in terms of conformal geometry. So what does that mean? We're going to define a conformal invariant. Well, this is a traditional way of doing it, which would say that with respect to that conformal invariant, that point or the set is small. Okay, so for those of you know that I'm going towards what's called polar sets or sets of zero capacity. Okay, and you can talk about point as well. Okay, so now given that, let's go a little bit and talk about what are conformal invariants. And before that, just let's on one slide remember what's a conformal map. So for me, conformal map is a function which, well, I guess this is not quite correct. So when I say conformal, it preserves angles, I also want to say it's injective. It's not just preserves angle, it's also injective. Okay, I should have added, it's a homeomorphism usually. And in all of these things, I'm assuming F is a homeomorphism. So maybe I should write down F is always, for me, it's going to be homeomorphism. Okay, so there are several different definitions. I'm sure all of you know these things. So, but that's what I mean. It means that it's a one-to-one onto map, which is analytic. So the derivative is never equal to zero. There is a derivative. Okay. So okay, so that's good. Now what we're going to talk about is the first conformal invariant that we're going to discuss. Before that, we're going to talk about Riemann mapping theorem. Everyone knows about it as the first most important theorem in complex analysis, probably, at least in the mapping theory, which says that if you have a simply connected domain in the plane, which is not the whole sphere, not the whole plane, then there is a conformal map onto the disk. Right? So, and then an important thing is that it is unique if you assume some normalization that at the point is equal to zero and the derivative at that point is positive. So this theorem,
What does it mean positive?
Huh?
P,
the derivative,
complex number.
yeah, it means it's positive.
Complex number positive.
Real.
Real.
Real positive in particular means real. Yes. So, so that if you think of it, you can rotate it so that it points in the right direction, right? So, so the others, there's lots of people who contributed to this because the way, of course, Riemann who formulated this was not like this at all. He didn't really know what it means to be or to have a general simply connected domain, and well, probably the first complete proof was given by Oswald. Anyway, so what we're gonna hear this week is some generalizations of Riemann's theorem and some very recent progress towards that. In particular, let me actually go back. So the more general version is Kobe-Poincare uniformization, which says that any simply connected Riemann surface is one of the three, is a Riemann sphere, disk, or the plane. And of course, it's clear that the sphere is not the same as the plane or the disk, but the fact that the disk and the plane are different is a little bit trickier because they are homeomorphic, but then there is no conformal mapping by Liouville's theorem, right? Okay, so more generally, the type problem for a non-compact simply connected Riemann surfaces is to determine whether X is conformal to one or the other. Okay, and just to illustrate that this is not a trivial problem, let me see if that's what I have. Right. So the type problem, just to relate to what we were talking about before, basically is to determine whether the Brownian motion on or the random walk on the surface is recurrent or not. Okay, so the type problem for a general Riemann surface. For non-compact surface, you have to figure out if it's the plane or the disk. Okay, just the first example is the following. So if you think this is kind of an easy problem, let's look at the problem here. Well, actually, I want to do. Here is the, well, that's on the next slide. Let me just do more general versions of Riemann mapping theorem. So Riemann circle domain is a domain that whose every component of the boundary is a point or a circle. So and then, so here's an example of a circle domain. Imagine you have something like this, and then you have a circle, and then you have points, and maybe other circles converging to it. So this you can think of topologically something equivalent to a counter set, and so on. So that's the complement of this would be an example of a circle domain. So what Kobe proved is that if you have a finitely connected domain, so think of it something like this, the complement of these things, then there is a conformal map onto something bounded by circles. Okay, and sorry, the point has to go to a point, so there is that inside of one. That's, if you saw the poster of our session, then that's kind of a picture of the Riemann mapping here, Kobe's mapping here. And there is also uniqueness, but I'm not going to talk about that. And then, so clearly this is a generalization of Riemann mapping theorem, right? Because if you have this one boundary component, then you can map it to something bounded by one circle. Okay, so and then Kobe conjectured that in fact every domain is conformal to a circle domain. Okay, so what's an example of something that's complicated and we don't know if it's complicated? Well, yeah, in general, anything which looks like a general domain like that can be also conformally equivalent to a circle domain. So what's the difference between the finite case, of course, that you have an arbitrary number of boundary components, and then it took about 70 or 80 years to show that you actually have Kobe's conjecture holds in the countably connected case. So one of the reasons I talked about this is because we have several talks related to that, right? So for instance, I know Abhishek will be talking about the generalization of this theorem, very recent one from last year, and then related things related to Kobe's conjecture. Just to mention that Kobe's conjecture is still open. But there has been quite a bit of progress in the recent years, recent maybe 10 years or something like that. And also there was very important progress with the theorem of Henshaw. And one of the tools that was introduced to do this is transboundary modulus, and Irina will be talking about that, right? Okay, so right, so there's lots of interesting problems, and it's a very nice field to get into right now. Okay, so now let's talk about one example where just to illustrate that it's not very easy to figure out whether the topological surface, well, actually, like a Riemann surface is a disk or a puncture, is an annulus or a punctured disk. So here is an example, conformal geometry near an isolated point, okay? Consider Riemann surface obtained as the quotient of the strip as follows. So let me draw the picture. Think of the strip. So I'm looking at the strip like this, right? And I'm doing an identification. A point here, x, is identified with a point fx plus I, right? This is my 0, this is the I, and this is my domain, okay? It's an infinite strip. Now I'm identifying like that. The resulting thing is what? It's a, topologically, it's an annulus, or, well, conformally, by Kobe's theorem, it's an annulus where this thing here could be either of this could be a coin. So it's one of those. It's either that or that conformally. Okay, and the type problem here is to figure out the conformal geometry near, well, I'd say infinity, and when you go towards that, to right, you want to figure out, depending on the function f, whether I have a puncture or I have a fixed r here, which is a positive number. Okay. Okay, so it's not really as trivial as may seem, because it's right. So I wrote here by Kobe's theorem, it's a doubly connected domain which is conformal to an annulus. Does everyone see that? Yeah. We have, if I'm identifying this point to that point, so that gives you one boundary component, that would be the outer disk. And then when I go outside, since every point here identified with a point here, I basically have curves which go around some point. And then I want to figure out whether those points basically shrink to 0, those curves, or they shrink to a circle. So just to illustrate, think of like a point here, and you have a curve in the quotient, that thing closes down. Okay, so then you want to show whether it goes to 0. Okay, and here are some examples of the function f. Okay, can someone give me an example where I get a puncture? Well, I don't know, it's kind of unfair to you, maybe you wouldn't know it. One of the easiest examples would be the function fx equals x, right? If I identify this point to that point, okay? If I do that, then what you get is actually the puncture disk. Okay, that's actually not too hard to see, but I'll tell you how to do that in a second. And another example, let me see if I have this. Right, so these are one of the two possibilities, right? And the other situation would be, so let's call that f1x and f2x, let's call this to be 2x. Okay? So it turns out it's very, very different. If you have x, you get a puncture. If you get 2x, you get an arrows. Okay? And in fact, in general, you can say, okay, let's say your function f, fx equals x plus some function phi x. It really depends how fast this function grows or doesn't grow. So in this case, it's 0. In the other case, it's x, right? Okay, so how do you prove something? Okay, there's a couple of ways to do that. There's like ways which are you don't really need to use any modulus, but since we have a lot of modulus in our talks, I'm going to talk about that. So this is one of the most important conformal invariants. So this is called conformal modulus, and it was introduced by Berling and Alfors. So the first papers in 50s, but they were kind of similar things in the papers of Roche before, from 20s even. So if you read Johann Heinemann's book, he traces that back to Maxwell from to 1800s. So because it's just like the flow and the electricity and things like that. So okay, so what is this? So think of having a family of curves in a domain, right? I don't know how they look like, maybe like that. And the modulus of that curve family, this is called gamma. So the modulus of that curve family is defined as follows. You take the infimum of rho squared dx dy, where the infimum is taken over all those rows, such that the integral over every curve is at least 1. Okay, so why such a strange thing? So it's a variational thing. So in reality, it's not a very strange thing. It's a very natural thing, because even though it's called modulus in all the other fields, it has many other names like energy, like flow, many other things. But the key thing for us is that it is conformally invariant notion. So what do I mean by that? It means the following. Suppose you have a function from one domain to another, which is conformal, right? So let's say you have one domain and you map it to another domain. And let's look at the curve family, which connects, let's say, E to F, right? This is your gamma. Well, all of them is capital gamma in this domain omega. So you have modulus of gamma E F inside omega. So this notation means I'm looking at the curves connecting E to F, which are on the boundary inside the domain omega. Now let's say we have a conformal map F, and this is different F, so let me just call it capital F. And the image of the boundary arcs is going to be f of, oh, that's a bad notation. Let's call it phi like this. Phi of E, and then I have P of F. And F is conformal, right? So then you look at the curves connecting here. It turns out that the modulus of this is actually equal to modulus of the phi of gamma, phi of E, phi of F, and inside this, let's call this omega prime. Okay, so it's a conformally invariant notion. So this is very easy to prove, not very hard. It's essentially change of variables. Then the only reason it works is because I have exponent 2 here. If you take a different exponent, that won't be a conformal invariant anymore. If you do this thing in higher dimensions, you can get a conformal invariant in there as well. Then you would have, like, for instance, in R3, it has to be 3. You have generalizations of these to families of measures, families of surfaces, and things like that. And there are experts in the audience who know all of these things, but they are very useful. Okay, so what's the use of this in our situation? Right. So, yeah, here is one more thing, is that the picture didn't display right for some reason. Modulus can be thought of geometrically. Okay, what is the number of the modulus which connects the blue curve, the blue continuum, to the red continuum in this domain? It turns out, if you have a conformal, there is a conformal map with which has the following property. It takes the blue to some sort of a circle and the red to another circle, and all the other boundary components become straight lines. Okay, radial, in fact. And it turns out that you can actually calculate the modulus as follows using this formula, which is basically the modulus gamma of the curves connecting inside of this, the blue to the red in this region is given exactly by 2 pi divided by logarithm of r over r, where r is the radius of the big one, and the smaller r is the radius of the small thing. Yeah, so that's what we have. So now, because we know this thing, we can ask if we can answer that question if the surface that we obtain after this kind of identifications, whether that's a puncture disk or it's a or it's an animus. Okay, and the way you do that is you have to figure out whether the family of curves starting here and going all the way to infinity, whether that has 0 modulus or positive modulus. Okay, and here is one way to see that, right? So in the way we can do, so, and then there is also this important property that if you have a family gamma and you have gamma star is the family of kind of transversal family which hits every curve from the original family, you have this reciprocity, that duality that is equal to 1 over the other. Okay, so in this particular case, what you can do is, for instance, let's do the example of fx equals x, right? So let's do this example, right? So then we're looking at the curves that go from a point x and then go at the point x plus I, right? And then it turns out that you can figure out that the modulus of this family is actually infinite. That's very easy to do. It's not very hard. What you have to do is just take rho to be in 1. And if you have 1, then the length of every curve that goes from here to here is actually 1, because it's greater than the length of its projection, right? So that, and then you integrate 1 over this whole strip, you get infinity. And that tells you that the modulus of curves in the thing that you're supposed to map this to conformally is infinite. So that means the inside thing is what? It's a point, right? So in this case, we get a point. On the other hand, if you do something like that, x goes to, let's call it x and x plus x, right? So you have a curve that goes like this. You can do some other function rho, which actually basically shows that the modulus of any curve that goes from here to here will be positive. So and the way you do it, you define your function, I believe, to be rho x1 to be, I think, like 1 over x or something. The idea is that if you integrate 1 over x over an interval of length x, you get at least 1. So if you have a function that's 1/x, so it gives 1 at least this, so that's admissible, then you integrate inside, but you get something that's positive, then turns out that the whole thing becomes the connecting modulus is positive, is finite, sorry, and then the separating modulus is finite. Okay, how much time do I have time, or you don't have? I have some. Okay. Okay, so does that kind of make sense, right, so far? So now what we did was talk a little bit about the conformal geometry of a point. And that was kind of the isolated point, right? So the point at infinity in one case, so you can say, what's there to talk about the geometry of a point? But in one case, you get a point, in the other case, you get the point blows up into a circle, okay? That was an isolated case. Now let's do another example. Okay. Actually, this was related, this is also related to conformal welding, but I want to go to first to another example. Let's do this one, okay? So let's talk about an example where you have non-isolated points. So here is one example. You have this set. So the way this is constructed, imagine I take the square. This is like -1 squared. So in each of these diagonal squares, I put a slit of length 1/2. So this is 2, this one is 1, and this one is 1/2. Okay, so there is 4 slits of length 1/2. And then you put inside the square in each of the diagonal squares of generation. And the next generation next to here, I put a slit of length that's half the diameter of the square length. Okay, so this one's 1/4, this one's 1/4, this one 1/8, and so on and so forth. Okay, so what I do here now, here's a question. By Hilbert's theorem, I know I can map this to what? To a circle domain, right? And I'm actually, in the case of this is the Henry-Schramm theorem, right? Countably connected case because I have countably many values. What happens to the center? What happens to 0? Okay, that's the question I'm interested in. This is another instance of conformal geometry near a point. Okay, okay. Here's a similar question. The same similar domain. I just put classes or crosses. Okay, and it turns out. Well, in both cases, I'm interested in the conformal geometry near the point. Where does it go to? Okay. Any ideas? Here is a hint. You get different answers. You don't get the same answer. In one example, you get that that point goes to a point, and in another case, one of those cases, you get this actually. Okay. Any guesses? Maybe I should see what I have. These both can be mapped conformally to circle domains. What happens to 0 is the boundary component corresponding to 0, a point or a non-trivial circle. Okay. Can we use modulus to answer this? That's not, because we did it in the previous case. We can ask, can we use modulus? And the answer is no, we cannot. What we have to use is a version of a modulus that you'll be talking about, which is the transboundary modulus, okay? So modulus of curves in both of these examples is going to be 0 because there is so many slits, it turns out, or boundary components that the curves cannot really reach the origin, okay? So what do? For this, we use this kind of thing called transboundary modulus, due to Schramm. It's almost the same thing, but what you do is you add weights to all the boundary components. So your curve, if it passes through a boundary point, you add a weight to it. So that's the admissibility condition, and the weight is like that. So it turns out in this example, let me just go back. But right, so what happens to 0? Can we use now the transboundary modulus instead of regular modulus? And the answer is yes. Okay, transboundary modulus of curves connecting the boundary of the square of this square to the origin in that example is actually 0. And in this case, it's actually positive.
Can you repeat what was the problem of the modulus? I mean,
What do you mean?
what was why we can't use modulus?
Oh, because regular modulus is 0 for both.
Okay, but wasn't modulus an invariant? Like
It is an invariant,
So
yes,
it-
it's variant, but it says invariant at 0, so it doesn't distinguish between this and that. It's exactly correct. It's an invariant, but it's a useless invariant in this example. Okay?
Needs neater.
It needs like more stuff, so that's why a lot of things can be done using regular modulus. Okay? So in this example, we have that. Okay. So it's not very easy to do this computation, but one of the things you can do is like if you look at the square here, the modulus of curves going from right to left is actually going to 0, but on the other direction, there is lots of curves going, which is positive. In this other case, the modulus in both directions is 0, but if you look now transboundary modulus, it becomes, it's very symmetric, so it actually they both are equal to each other, right? And non-zero, that's important.
So if the transboundary
Yeah, this is the picture. See, if you take this, you map it, you no longer you get slits, but you get kind of squarish things. That's what you get for transboundary modulus. So the question is exactly your question, whether R is, but not in the pre-image, but in the image, whether it's positive or not. And the way to do that is, well, how do you calculate it from here? That's hard. Because well, it doesn't really seem any different here and here. In both cases, I have 0, okay? And it's kind of a hard computation, well, different thing to do modulus here. And this case, it's also not very easy because what you do is you actually use the geometry of the thing. Okay, so this is what I wanted to talk about conformal geometry of point, but I want to relate it to the talks about weldings, which is our talks, I think, on Wednesday, maybe. Okay, so this is what I had before. Remember when we talked about, oh, here, we talked about the punctured disc, when you take a strip, and then identify two different things. So you construct, right? So,
Hello.
okay. So it's kind of similar. This is a version of what's called conformal welding. So let's do
Hello.
the following
Can you
example.
hear me?
Yes? Oh, really? Is that you?
Yeah, we cannot see the slide. Slide is missing.
Oh, slides is not working. Let's try to make sure they work. Better?
No, yes, thank you.
Okay. So now we consider a strip again. This is an infinite strip. And now identify the top and bottom by a function x goes to fx. So this is a similar picture to what I had before, which is you take now infinite strip, you take a function that takes x and then identifies to something which is fx plus line. So this is a real line, this is the line through I. So you want to identify this to that. And then the question is SF the resulting thing, which is topologically is a tube or an annulus, is it conformal to an annulus? Okay, so that's one way to talk about just to what's called a welding. It's not the usual way, so those of you who are talking about conformal welding may not realize this, but here is the, I'm just gonna talk about the next slide and be done with it.
Does it work?
Does it work? How do I do that? Okay, yeah. Here is the standard way of talking about welding, okay? What you have, what is conformal welding? Conformal welding is the following question. Suppose you have two discs, and you can think of them as hemispheres. Right? So those of you who have seen Bishop's paper, he does it kind of like this. And now, this is my disc one, and this is your disc two. And what you have is a function, a homeomorphism, which to every point here creates a point, well, corresponds to a point here. So I have a homeomorphism of the circle. So what do I get? I take the quotient of this union, which topologically is a sphere. That's a theorem of Moore, I believe, right? So, so topologically it's a sphere, and the question is, do you get actually a conformal structure on this? Do you get an actual sphere on this? And that's a big question. What that means, what that turns out to be equivalent to is the following. In the following question, suppose you have, well, a curve gamma, and then you have domains W1 and W2, and for both of those, you have, well, sorry, this is supposed to be the remaining thing. One is going from inside to inside, the other one is going to F and H, I guess. Right, F and H. So you have conformal map from here, from inside to inside, and you have a conformal map from outside to outside. And what you want to say is that if you compose, this is, I didn't say, this is a Jordan domain, Jordan curve. So that means if it's a Jordan curve by Carathéodory's theorem, I don't know if all of you know what Carathéodory theorem is, it says that there is an extension, continuous one-to-one extension to the boundary, right? So then you can extend both of these functions to the boundary, and then because of that, you can define the function h, which is f composed h inverse. Right? Okay? And then the question is there a curve so that if you do this procedure, you get your function h? That's the question which is called the conformal welding question. So it is true that given any Jordan curve, you can find a corresponding homeomorphism welding, but it's a completely different question whether given a homeomorphism, there is a curve. And it turns out, I think in some of the talks, there will be an example showing that you can have a homeomorphism which doesn't produce curves. And well, there's lots of things related to that, lots of research related to that, lots of recent research, especially in things related to probability theory, strangely enough. right? So if you heard about what's that about?
Just the homomorphism without additional equipment.
Yes, yes, absolutely. If it's a diffeomorphism, it's true, even if it's quasi-symmetric, it's true, right? Right, so there will be a talk about that as well. So that's my kind of pitch about the conformal geometry of curves. I didn't get to surfaces. I did get a little bit to the surfaces, but that was our original motivation to talk about surfaces. But well, you do get the surface because when you glue two discs along a curve, what you get is a sphere. So that's the question: do you get a sphere or you do not? Okay. So, I mean, if I had time, I would give examples. In fact, the very first example that I gave about the strip, it actually produces a very simple example showing that a homeomorphism which doesn't give a welding, and locally what that is if you take a function which looks like x here but x squared here near zero, if this is your zero and your function looks like x on one side and x squared on the other side, it turns out that that function cannot produce a welding. It is not a welding, okay? And it's very much related to the question I was telling you before, the one about the points, okay, when you want to have the strip. Okay, so if you had any questions about any of these, yeah, we'll be happy to talk.
Is there a sufficient necessary condition for welding?
Well, that's the $1,000,000 question. I don't know if it's $1,000,000, but it's like that.
So maybe there is a sufficient but not necessary.
Well, there's definitely sufficient conditions. Like there's quasi-symmetry, there is.
Quasi-symmetry is the weakest.
It is not the weakest. You can have much worse
That's
things,
what
which are these things. Who's talking about log singular functions? Someone's talking, yeah, exactly. So there is log singular functions of Bishop which produce. So that's sufficient conditions if you have. I mean, quasi-symmetries produce quasi-circles which are able, huh?
Is there a conjecture?
No, even that's not there. I think
I
that,
have a question.
yes,
Can you please go to the slides where you have constructed the a domain by removing countable many
yes,
slits?
the slits, this
Yeah.
one, or the
Yes.
box?
Yeah. This is the correct. So I don't know the question makes sense or not, but if here you are removing countable many slits, what will happen if we remove countable many, let's say, rectangles? So instead of slits, we remove rectangle.
Well, you can do that too, right? So it depends what kind. You can do like thin rectangles. And in this case, you can probably arrange them so that they don't even intersect.
Yes.
Yeah, so that would be a similar thing. In this example, I know I can show that the modulus of curves in the small square goes kind of horizontally, that goes to zero. But the same thing would be true for the rectangles as well.
Okay. Okay. Thank you.
Yeah. Okay, I think I have a lot of stuff. As you can see, I went through 20 pages out of 16, or maybe a little more. But I think this is probably a good place to stop. So I'm gonna stop here and then if you have questions, I'll be happy to answer any questions.